Hey, welcome to the second video on transformations of graphs. In this video, we're going to talk about compressions and stretches. So for our first example, we're going to look at the graph of f of x equals 3x squared. And we'll start with just looking at a table of values. Now we can have x squared, and 3x squared. And maybe we're interested in the points 0, 1, 2, and 3. So if we plug in 0 to either of these functions, we get 0 out. If we plug in 1, 1 squared is 1, and 3 times 1 squared is 3. 2 squared is 4, but 3 times 2 squared is 12. And for 3, we get 9 and 27. So before, when we were looking at translations, everything just had a constant value being added to it. So for instance, x squared plus 1, every value we outputted just added 1. But now we're not adding, we're multiplying every point. So this one's multiplied by 3 to get 3. This one's again multiplied by 3 to get 12. The same with 9 and 0. So what this ends up looking like on our graph is we can start with our usual quadratic. So this is a poor drawing of f of x equals x squared. And just because we already talked about f of x, let's call this one actually g of x equals x squared. And now for f of x, any y value on here, let's say that's y, we're actually going to go up to 3y and make a new point, and that will be our value. And so our new quadratic ends up looking something like this, where it's always 3 times greater for each point than what it was before. We can do a similar thing with g of x equals 1/5 absolute value of x, where if we draw the graph of the absolute value of x, our new graph is just going to look a lot flatter, like it's been compressed down. Where instead of, if this is 5, then up here we would have 5, and this new point down here would be 1. So with the original graph, the absolute value of 5 is 5, but 1/5 times the absolute value of 5 is only 1. And so that's a compression. And above is a stretch. And so a stretching or compressing is just a constant times our function. So the function f is stretched / compressed if it is multiplied by a constant a So then AF of x is the stretched or compressed version. And mostly it's just terminology, where it's stretched if A is greater than 1 and compressed if A is less than 1, just because of how the graph looks. It doesn't really make sense to say stretched if you're making something smaller. So we use compressed instead. And this is also helpful to just look at Desmos to see how it changes. So we'll do that next. I'm going to stop sharing and share Desmos. So if we have f of x equals x squared, we'll just leave that there and we'll create a new function where we can just type in AF of x and click this add slider for A. And we can see when A is 1, 1 times f of x is just f of x, so that stays the same. But as we change A, we make A 1/2, this resulting blue function is our compressed version. So everywhere you look, it's a little bit smaller. And as A becomes even smaller, it's more compressed. But as A becomes bigger, it gets stretched out. In the next video, we'll talk about what happens when A is negative. And we'll look at another example as well, where if we have, let's say we take square root of x. Then as we alter A, we can see the square root is just moving, it's being stretched up or being compressed closer to the x-axis as A changes. All right, well, I think now would be a good time to just practice graphing different versions of stretched or compressed functions.